Morning, everybody. Thank you for joining us today for our webinar short course today. This is one of a series of events that we host like this. I'm here from EUMETSAT. I'm Hayley King. I'm the lead marine applications expert in our user support division here. And it's my pleasure to introduce the webinar short course to you today and to introduce some of our colleagues from the OSI SAF who are going to tell you more about their sea ice climate records. I'm just going to start with a very short presentation, a little bit about who we are at EUMETSAT. Some of you may already be very familiar with us, but for those who aren't, you can learn a little bit about who we are and what we do. And I'll share with you the agenda. I will proceed with regards to answering any questions that you have during this webinar today. So who are EUMETSAT? This is us in this building that you see here, based in Darmstadt, Germany. We are the European Organization for the Exploitation of Meteorological Satellites. We're a member state organization, so we represent the interests of 30 different countries. The main aim that we have is to provide observations and data for operational weather system monitoring and forecasting and for climate services to those member states. We also have other work that we do underneath the Copernicus program. Some of you may have seen me in some of the short courses on our marine data streams from there. And beyond what we do in the building, we also have a key partner when it comes to the ocean and sea ice world, and that is our OSI SAF, the Ocean and Sea Ice Satellite Application Facility. We work with the data we provide from our satellites and produce further downstream services. You'll hear a lot more about them in a minute. In terms of the short courses, we provide these courses on a range of different types of data, applications, as well as tools. You can see previous courses, the recordings of them at classroom.eumetsat.int, probably where you went to register for this one today, as well as upcoming courses that you can register for in the future. This is an open and collaborative series, so if you have ideas of courses that you'd like to see, or if you'd like to collaborate on one of those with us, if you're working with our data or something, we'd be very happy to talk to you. So you can email us at training@eumetsat.int to discuss more. So today's webinar agenda is as follows. A welcome introduction from me. Thank you all for joining us. And then Gwen is going to talk a bit about the OSI SAF itself and the work that they do. He'll then hand over to Thomas, who's going to talk about the sea ice concentration climate data records, followed shortly by Emily, talking about the drift climate data record, and finally Signe, who will talk about the sea ice index. Finally, Thomas will share a practical demo on data access and basic use. Then at the end of the webinar, we will be able to answer any questions you have about the data, our services, anything broadly as well. And for this, we'll be using Slido. So if you'd like to sign into Slido, you can go to sli.do. You can use the hash EUMSC45, and you'll see our Q&A session there. And you can also scan the QR code that's on screen at the moment to join that. You can put your questions in as we go through the webinar today, and also at the end when we have the specific session. You can also vote for questions you'd like to be answered. Finally, we'll also have a feedback questionnaire at the end, which we ask you to fill in after you've gone through the webinar today. This feedback is super valuable for us. It allows us to know if we're providing the right information for you in these webinars and to help us improve and justify doing more of them in the future. So please do fill that in. As I said before, if you have any questions about the training or anything else you'd like to talk to us about, you can use training@eumetsat.int as an email to contact us. And before I finish, I'll just make a couple of adverts for upcoming things. If you're attending the Ocean Optics Conference in October, we'll be running some short courses at this event you might be interested in, so you can register through the conference website if you're attending. We also have our first Marine User Days event coming up in November in Lisbon, Portugal on the 5th and 6th. This is a free and open event for you to attend. It's only in person, but this will be a chance to get together with people from across the marine data providing community in Europe. So ourselves plus our colleagues from across the Copernicus program and beyond, and to talk about different ways that we can use satellite data for the benefit of our marine environment. So if this is something of interest to you, I'd very much encourage you to apply. You can find the information on our website. But generally, more information about any upcoming training courses, you can find at trainingevents.eumetsat.int. This is our training calendar. And that is everything from me. So I will hand over now to Gwen. Gwen, are you there?
Let me first share my screen. And up. Let's go. So you all see my screen, I hope.
Yes, all fine.
Yeah. My name is Gwenaël Le Bras. I'm the Communication and Outreach Officer for OSI SAF, and I'm going to present you shortly what is actually the OSI SAF and what are we doing about sea ice. So the OSI SAF, as said Christine, is the Ocean and Sea Ice Satellite Application Facility. It's a collaboration of Meteorological Institute in the member states of EUMETSAT that concentrate then on the ocean and sea ice satellite observation. And we produce and distribute data about sea ice, sea surface temperature, ocean winds, radiative fluxes from the ocean, and to soon come about the ocean color. As you see on the map, we have 5 organizations collaborating in France, the Netherlands, the Denmark, and Norwegian. And today, our colleagues from the Norwegian Meteorological Institute are gonna present the climate data record on sea ice. So, what are we producing when we speak about sea ice products? We do produce satellite observation about sea ice concentration, which Thomas will speak longer about later. From the sea ice concentration products, we do as well, our Norwegian team is doing as well a sea ice index, which Signe will talk to you a bit more later. Then we have a second group of products that are about the drift of the ice, the full monitoring the drift of the ice over the pole, which Emily will talk to you about later. Then we have 3 other family of products: Sea Ice Edge, which is the edge of the ice in both pole, and Sea Ice Type, which is the class age of the ice, either it's from the year or older than 1 year. And we have the sea ice emissivity. These three product families don't have a climate data record to be shown. They are only near real-time products. So since I'm on it, what is the difference of near real-time and climate product? Near real-time is the basic data that do produce and distribute OSI SAF and more generally EUMETSAT. Like, we are a meteorological data producer at first. So near real-time will be the data we produce with the shortest time between the satellite observation and the distribution to the user. So here on the sea ice, or L2 data, the most basic one we distribute will be less than 3 hours and 40 minutes. And for L3, a bit more elaborated one, there will be between 5 and 6 hours max between the satellite observation and the distribution to the user. Numerical weather prediction needs this time to be as short as possible. But then, of course, if I click correct, then of course things produced fast may hold more issues, more inaccuracy. So once we have this data, we are from this data producing through algorithm, taking time to produce more reliable data that we name climate data record. And we have like 2 types of climate data record: the actual climate data record that will be a reprocess of our data on a long a long period, but it will have a date of beginning and a date of end. So like for the sea ice concentration climate data record, the third version, it's between 1978 and 2020. And then on some products on sea ice concentration, actually, we do have as well what we call interim CDR, which are using the same algorithm to produce day-by-day data, but with a latency of almost 2 weeks. And then to fill the gap, we have what we call the fast track files that takes 2 days that are produced with a latency of 2 days that we are distributing as well, but they are temporary as they may be a bit less accurate than the 2 weeks delay data from the ICDR. So if you want to use our data, please register to our website. This for 2 reasons. First, for us, we like to know who is actually using our data, and that's a way to have an idea of it. So, and as well for you, we are distributing announcement regarding to this to our products in case there is a problem that we noticed or something like that, or an interruption of distribution or stuff like that. And so we will ask you to please register to on our website, oc/saf.umetsat.int/register. And as well as everyone, we like to have feedback on our data, so don't hesitate to contact us by using ticket help desk on our website. So if you have any questions on the actual products, but as well if you have feedbacks to give, please contact us through the website. So that was it for my side. I will hand over the speech to Thomas that will present you the sea ice concentration climate data records. If is
indeed.
Okay.
Thank you, Gwenaël. Good afternoon,
Hi,
everybody. Very nice to see you here, wanting to learn more about our sea ice climate data records. So my name is Thomas Lavergne. I'm at the Norwegian Met Institute, working for the OSI SAF, among others. I'm going to present to you shortly about the sea ice concentration climate data records. And so this is me, but also in the background, my colleague Atle Sørensen is really the one doing the number crunching. And so it's very nicely thanks to him that you have these NetCDF data files available. That's the overview of what we're going to go through with me. That's the why do we have sea ice concentration climate data records, how we make the climate data records, also what are the limitations, and then what we plan to do for as future developments towards the next version. So why do we do our climate data records? Well, sea ice is changing at the polar regions with the climate is changing. So sea ice concentration is an essential climate variable, an ECV, of the global climate observing system, GCOS. And sea ice extent that is derived from concentration is a WMO headline indicator of climate change. In the IPCC RS6 Working Group 1 report, they could assess that human influence is very likely the main driver of the decrease of Arctic sea ice area, and they could give numbers for this decrease in September and in March, and they could do that thanks to satellite data. And if you've been following as well in the Antarctic, after a period of stable and even slightly increasing trends, Arctic sea ice area really abruptly dropped after 2014, 2015, and now with record low values last year and still low this year. So it's important to keep monitoring the sea ice and we do that best with satellite data in a climate consistent perspective. Of course, climate data records of sea ice concentration are maintained by several agencies. So the OSI SAF data record is one of the multiple lines of evidence that the polar sea ice cover is changing. In this table, I'm summarizing the 3 climate data records of sea ice concentration that OSI SAF currently has. On the first column, you have OSI 450A. This is our climate data record that extends from 1978 to the end of 2020. It is done with SMMR, SSMI, and SSMIS data. In the second column, you have OSI 430A. This is our interim climate data record. So this is the processing chain that has exactly the same algorithms as the CDR, but with a latency, and extends the CDR to the present day. And finally, to the right, you have OSI 458 that has very similar algorithms than the other two, but achieves a higher resolution thanks to using IMSR-E and IMSR-2 data. You will note that because it's using the IMSR-E and IMSR-2, it is also shorter. It starts in 2002. But other than that, those climate data records are made very similar to each other. The content is the same. You have sea ice concentration, the uncertainties, some status flags. You have 1 file per day with the northern hemisphere, 1 file per day for the southern hemisphere. And if you go to the bottom, we have an east to 25-kilometer grid for all of our data. To the left, you see a false color composite of brightness temperatures. So this is the raw data we use as input to all our algorithms. You will see, hopefully you can locate yourself. You will see that the ocean is darker than the ice, but over the ocean, you also see some yellowish shades. This is the impact of the weather. And on the ice, you see some different colors for the ice, the old ice, the new ice. This is the imprint of the ice type. And all these are noise to our retrieval. We are doing algorithms that can compensate for these noise sources and provide you only the ice concentration. What is very nice is that this type of data is available for a whole suite of satellite missions that you see to the right. You have a timeline of the passive microwave satellite missions that we are using. And so the blue box at the top are the SMMR and SSMI data that we're using for OSI 450A and OSI 430A. And at the bottom, you have the box that is for the IMSR-E, so for OSI 458. And you see that there is no temporal extension of OSI 458. It is a climate data record that ends at the end of 2020. Here are examples of sea ice concentration maps. To the left, you have an example from September 1980. In the middle, a few days ago, in September of 2024. So that's the power of having a continuous update to the climate data record. To the right, you see 2 zooms of the Ross Sea. One at the top from OSI 450A. You see the coarse resolution with respect to the example below from OSI 458. Which is from IMSRs and have better resolution at the ice edge, along the coast, and in the ice pack. So how do we do our sea ice concentration retrieval? To the right, you have again an example, a false color composite of the brightness temperatures. That's our raw data. And we start from this raw data, and the first thing we do is we correct it for the contamination by the atmosphere and by the land. Then we do our sea ice concentration processing ourselves with our own algorithms, where the ESA CCI program contributed with R&D. This gives us level 2 sea ice concentration and the uncertainties for all pixels in all orbits over more than 40 years. We finally composite those ice concentration into daily maps, level 3, and then we fill the gap. This is level 4. And we distribute the level 4 data. So this is basically how we go from the raw data to ice concentration. It's not easy to validate sea ice concentration. We don't have a lot of validation data. We try our best. What we show here is a time series of the uncertainty, so the one standard deviation of the uncertainty over open water and low ice concentration conditions. And I want you to focus on this more solid line here, which is around 2%. This is what we can document is the uncertainty of our ice concentration product at low frequency, at low concentration, sorry. Over high concentration, this is also complicated to find good validation data, but using SAR sea ice drift in the ESA CCI project, we can assess where there is 100% sea ice, and when we compare our climate data records, we see that we have RMSEs around 3 to 4%. We have a small bias in the Arctic, improving from previous version, and we have no bias in the Antarctic. There are known limitations to the sea ice concentration climate data records, mostly because they come from passive microwave missions. The early decade, so from 78 to 87, has long data gaps and interruptions. So if you're using that decade, and so please look at the status flag so that you can see where we have interpolated values. There is residual false ice along the coasts, so especially in lakes and smaller seas, that there is residual false ice, but things are better with OSI 458. And in summer, the surface melt and the wetter atmosphere contaminate the signal, so we have higher uncertainty. All this is described in the product user manual, and we invite you to read it. So now future developments towards V4. So first of all, we distributed V3 only last year. So we really want to hear from our users what you liked and what we could improve before we're going to prepare version 4. But still in version 4, we would like to have higher resolution, at least for part of the time period. That is an R&D that has been demonstrated in ESA CCI and that we could take on board the OSI SAF. We would like better accuracy by using a better radiative transfer model and better interpolation of the data gaps. Now, I told you that RMSR CDR OSI 458 had no continuation, and this is correct. There is no official continuation, but we are actually already running a prototype production of the extension, so starting 2021 to today. And if you want access to this product, please contact us. In the meantime, we are making it an operational product. That's now showing your go-to page to get information about the sea ice concentration CDR. So it's from the OSI SAF website, and you get one page per product. And in that page, you have access to the product user manual, the algorithm theoretical basis document, the validation report. You have links to get the data and links to get to the quick look images. And if you click on this, they talk about it, you're sent to the excellent climate data guide from NCAR, where we really try to explain to our users what are the strong points and the weaknesses of this climate data record. So thank you for your attention. We're going to move now to my colleague Emily for the sea ice drift climate data record.
Hi, I'm going to talk about the sea ice drift. I'm Emily, and this is work done, really led by Thomas, who's actually just talked to you about the ice concentration climate data record. So the overview of the talk is going to say a little about the importance of this climate data record, how it's created, its limitations, future developments, and some example usages. So sea ice is very mobile, and it moves up to tens of kilometers per day, pushed by winds and currents, as you can see in this lovely animation. It transports ice to lower latitudes where that ice melts, redistributing the fresh water. It pushes ice together where it thickens and therefore can become more aged ice. And we know that climate change is resulting in faster sea ice drift over time, and therefore it's important to monitor this, and it's an essential climate variable. So this climate data record is a global product which has a Northern Hemisphere file and a Southern Hemisphere product file. It covers 30 years from 1991 to 2020 on an ease to 75-kilometer grid. In this product, each of these motion vectors covers a 24-hour period. So there's no finer detail of the motion within that period, but it's in single 24-hour period vectors. It's a year-round product that has reduced accuracy during the summer months. And I'll talk a bit more about the method in a minute. Here's one example of the product. So you can see in the colored fields inside the red box that these are the 4 product fields that come in the NetCDF files. There's X and Y components of the drift, then there's uncertainty and a status flag. So if you wish to retrieve the actual displacement, then you need to combine the X and Y components geometrically. So this climate data record is made with 2 main methods. So the primary method, which is the more accurate method and used in the winter months, is motion tracking. So for this, we use daily average maps of satellite signal from passive microwave instruments, SSMI and AMSAR. These are daily average maps. They have a Laplacian filter applied, which bring out the details of the ice. And then there's a pattern matching from 2 consecutive ones of these images. This method was developed as maximum cross-correlation, which used whole numbers of pixels, and Thomas Lavergne enhanced this method to continuous maximum cross-correlation, which matches with fractional pixels. So you can see in this image on the left how much smoother that vector field is than when you're matching only an integer number of pixels. And there's also a step in this technique to correct for erroneous vectors which clearly stick out as being wrong, and then they're corrected using neighboring vectors. So that's used for 6 months of the record, so across the winter period. And then there's a shorter summer period, which is gap filled. So in the summer, the main algorithm becomes less reliable due to meltwater on the ice and increased atmospheric water content. Then we use this free drift model, which assumes that the ice is just pushed around by wind and doesn't have any internal stresses. So with the ERA 5 wind reanalysis, we use as training data the most accurate of the original method, the continuous maximum cross-correlation ice vectors from the AMSAR satellite. And then training on this, we find some parameter fields per month from the inverse free drift model. Then we can use these parameter fields and the wind in the forward sense to retrieve the ice drift. So we validate with an independent method against unice drifting buoys, which are not in the original record at all. So they're not used as data, they're just validation. You can see that there's quite sparse buoy coverage in the Southern Hemisphere, whereas over a 10-year period, we have very high buoy coverage in the Northern Hemisphere. So the buoy vectors are co-located in time and position with the product vectors, and then we just compare the X and Y components of the drift to straight away get the RMSE of the product. In the winter period, where we're using multiple satellite sensors, we can then merge these together from AMSAR and SSMI using the uncertainty to give us an optimal merging. Then we interpolate for gap filling, and we blend across month-long spring and autumn seasons to get this merged product, which is a single file per day across the whole year. The RMSE of this multi-sensor product exceeds the target requirement of 5 kilometers per day for all seasons in both hemispheres. You can see, though, in the southern hemisphere only, there is a bias where we're not completely capturing the fastest of the ice drift vectors. So there is that bias. That leads me on to the limitations of the CDR. And apart from this southern hemisphere bias, we also find that we have a bias in the summer ice drift from the free drift model in both hemispheres. There's also lower drift accuracy in coastal areas, and we're also limited to this 30-year period and limited in spatial resolution. So in the future, the wish list is that we extend this CDR back in time using the coarser resolution satellite data from SMR. We want to extend forwards with an interim climate data record, investigate if we can improve the spatial resolution of this product. We also want to investigate the bias in the southern hemisphere drift and see if we can improve that, improve the tuning of this free drift model, which gives us the bias in the summer, and create an improved uncertainty model. The most common question we get is people who wish to use, who wish for more modern data than this CDR that ends in 2020. So we are hoping to extend with an interim climate data record, but since there's no timeline on this, you can in the meantime use the near real time product. It has different gridding, it's on different format, different duration drift vectors. So there are caveats to it, but there is a notebook which can help you as a starting point to join these data sets. Very quickly, I just want to touch on a couple of example usages for this drift data. So you can use this ice drift to basically check what's happened to this ice historically. So if you trace back in time using the daily drift and checking the concentration each day, then you can find where the ice originated. So when you reach an area of low certain threshold of ice concentration, you can assume that the ice was formed there. So here's a plot of this, which, and we're creating a public software package for this purpose in the Sudoku project, so that is coming soon. In a very similar way, you can use ice drift to determine ice age. So you're combining the ice concentration together with the ice drift, and you can either retrieve fractional maps of ice age or probability maps of the age. Finally, I'll just show the OSI SAF webpage for this product, which gives you all the information you actually need to know. So the product user manual, the algorithm theoretical basis document, validation report, quick looks and data. And of course, if you've got any questions, please contact. Thank you. And now it's Signe Aaboe to talk about the sea ice extent. Oh, I didn't turn on.
Yeah.
Okay. So I guess I just continue, and good afternoon to everybody, and thanks for staying. So my name is Signe Aaboe, and I'm also working at Met Norway together with Emily and Thomas. And I'm here to talk about the sea ice index that we provide in the OSI SAF. In fact, we have actually provided the sea ice index since 2012, but it have had several upgrades recently last year. And several colleagues have contributed to this, especially Thomas and Atle Sørensen from our team together with me. So first, the importance of sea ice indexes. So sea ice extent, or sea ice extent, which is derived from the sea ice concentration, is a headline indicator for climate change and is often used in high-level climate assessment reports, like the IPCC, and also in several annual climate state reports. Most of you have probably seen figures like the one on this slide, showing the Arctic sea ice extent. Here is shown from two different sources, the OSI SAF and the NSIDC. In the orange colors shows the time series of September sea ice extent back to the end of the 1970s and up until now. And in blue is the winter March sea ice extent. Also, the state of sea ice in a seasonal perspective is often interesting news items where we report about the maximum and minimum situation. Right now, we are going towards a minimum situation in the Northern Hemisphere. And here's just two examples picked out showing the Northern Hemisphere to the left and the global sea ice extent to the right. And at present, we actually have low sea ice extent in the Northern Hemisphere, in the Southern Hemisphere, and adding up to give us record low sea ice extent in the global setting. So what is sea ice index and how do we calculate it? So we often differ between two different terms, the sea ice area and the sea ice extent. So the sea ice area, which is illustrated here in the figure to the left, is the actual area covered by sea ice. So in the illustration, we have 4 grid cells, which contains different sea ice concentration, each of them, and adding up the areas of these sea ice gives us for the sea ice area 1.75 square meters. Whereas the sea ice extent is the area of grid cells in which the sea ice concentration is above some threshold. Normally we use 15% sea ice concentration. It's very common to use. So for the sea ice extent, for the same sea ice conditions, we get 3 square meters. So in general, the sea ice extent is larger than the sea ice area. And it's most commonly used to use the sea ice extent. Also, it's typical to calculate the sea ice indexes for the entire hemisphere, for the Northern Hemisphere or the Southern Hemisphere, and add these together to the global situation. But it's not always that the hemispheric index is representative for smaller regions, since this is actually a floating media and it can move around in different years. So I give in this slide an example that the 2007 was a year where the summer sea ice in the Arctic was extremely low, which is highlighted here with a red circle in the time series. But if you look at the anomaly map to the right, you see that the missing sea ice was mainly towards the East Siberian side or the Alaskan side, where we were completely missing sea ice relative to the normal climatological average. But if you look in the European sector, in the Fram Strait and south of Fram Strait in the Greenland Sea, for this summer situation, we actually had more sea ice than was normal. So therefore, we have, for the recent version of the sea ice index, we have included also regional ice indexes. So here's an overview. Here's all the information you need to know. This is in the OSI SAF setting, it has the ID OSI 420. We are now at the version 2.2, which we released last year. It's based on the latest version of the sea ice concentration, CDR and ICDR that Thomas just presented. We provide both the global, the hemispheric, and also regional ice indexes. The regional ice indexes are defined from latitude, longitude bounded boxes. It has the same temporal coverage as the sea ice concentration, which goes back to October 1978 and up till present, and it has a latency of 1 day. We provide both the daily and the monthly sea ice indexes, and also we do some statistics, basically the means and the trends, which are available in the graphics themselves. So in the data files, they consist of estimates of the sea ice extent, the sea ice area, and also a processing status flag. And we provide the data both in ASCII text files and also in NetCDF files. As a supplement to the data files, we also provide daily updated graphics on the time series, and we also do a rank table. In addition, Met Norway has released an interactive plotting tool on our webpage, creo.met.no, where you can go and adjust your plotting as you wish. So I recommend to take a look at that. We are already now in a progress of updating the sea ice index to a version 3, which will be the first official operational sea ice index. It will be based on the same input data, but we have several larger upgrades, and these are highlighted here in blue. So we have a slightly different definition of the regional indexes. We do a lot more statistical estimates, which are listed here. And from version 3, the statistics are actually included in the data files themselves, in addition to in the graphics. And to give a more spatial context of the sea ice index, we also, from version 3, provide climatology maps of sea ice concentration. So when you download or when you use the sea ice index from OSI SAF, you should know that it consists mainly of values based on the sea ice concentration CDR. This is fixed calculations. Then it's supplemented by the daily updated calculations from the ICDR. Here it's important to note that these values are calibrated against the CDR because we have some known differences in the input data that we try to filter out. For the last 16 days, we use the fast track ICDR data from concentration. And here it's important to note that these estimates will be continuously overwritten by the ICDR data. In the data file, the input data, what kind of input data that is used is marked in the status flag. For validation, since the sea ice extent and sea ice area is not something we directly observe, but this is an index that are calculated from ice concentration, we don't really have any observations we can validate against. Instead, we do comparison to other existing similar indexes, and we are especially interested to see if the trends are similar across the different indexes. So if they do compare, this is gives some robustness of the values, but it's very important that we know the details of each retrieval we are comparing to. For instance, it is very important to know how the different retrievals have treated the gap hole in the North Pole or other details, because this will actually make a big difference in the ice index calculations if we include the pole hole or not. This is why you see a larger disagreement in the beginning of the time series in the figure below. So how do we actually assess the comparisons to actually see if two values compare well or not? We wish to have some uncertainty values or uncertainty ranges, and by now there's a lack of uncertainty estimates on any of the existing sea ice indexes. This is something we are planning to work with, or we have already started that work in version 3, and we will provide uncertainty estimates on our monthly sea ice indexes. Finally, I will just show some of these climatology maps that we will provide for the upcoming version 3. So it will basically be the sea ice concentration with a climatology contour for reference. It will be anomaly maps, and it will be trend maps. And my final slide here shows the product page from the OSI SAF webpage. You see the URL at the top. And here you find all information about the status, description of the product. You will find link to the product user manual, and later we will have the ATBD and the validation report. You find where you access the data, and you will see where you can see the quick looks, and also you can find this interactive plotting tool. So that's all about the CIS index, and you're welcome to ask questions in the Slido. Now I'll give the presentation back to Thomas. Thank you very much.
All right, so the final presentation, thank you for still being there. The final presentation is not about how we do our products, but we want to show you maybe how to easily access and use them. We can't go through all the examples, and there are several more notebooks that were made to teach how to use the OSI SAF CIS product. You can find them, for example, on the EUMETSAT training resources and the EUMETSAT GitLab. But here I present two Python notebooks from my own personal GitHub repository. So here is a URL, it will be communicated, and maybe it can be in the chat later. But these are two examples of what I call snippets, so small examples how to use the data. The first one is how to read pH concentration files from different resources. I hope you see that on the screen now. So as I presented, we have several CIS concentration climate data records at the OSI SAF. We have the three first one, and then this notebook will guide you how to read the data even without downloading the files, and do some simple plotting. In addition, we support the CCI high resolution SSMI climate data record that is an R&D CDR that has the same format but made from the ESA CCI. So you import what you need. Here we're going to use the X-array module and mostly matplotlib to do the plotting. Follows a number of routines that will find for you the URL where the data lives. So here it's important, we are not going to download any file. We are going to use the OpenDAP protocol to directly read data from the cloud. So these are basically how to find the URL. And if I scroll down and ask for the files corresponding to the 15th of September 2007 for the Northern Hemisphere for different sources, you will see that the routines will get you the URL. And so without downloading the files, you can ask X-array to directly access the data through the URL and to print the dataset, and you get the content of the NetTDF file with its time and X and Y dimension. You have the ice concentration, you have the uncertainties, the status flag, and all the attributes. From there, we can do a simple plot, just showing an image view of the field without even considering a reprojection. You have one example, you have another example where I composited a Northern Hemisphere and a Southern Hemisphere quick look. Obviously, you can then add some text or some more details. Then another example where you do the same. So you open the X-array dataset directly from the URL for two dates, one in the 1980s and one from very recently in 2024. And you plot the contour of the ice concentration. This is what you get. So it's very lightweight to access the data for some days without downloading the data. Then we can choose one day, so 24th of August 2020 for the Southern Hemisphere, and we read three different climate data records, the one from the OSI SAF from SSMI, the one from the OSI SAF but using IMSR, and the one for ESA CCI. You can plot the three side by side, and you see that to the left, the OSI SAF climate data record from SSMI has coarse resolution, higher resolution with IMSR, and similar resolution with ESA CCI+. The ESA CCI Plus is a 30 years climate data record that was done in ESA CCI. And I invite you also to take a look. It might be the answer to your research question. And finally, we are here accessing 3 recent dates. So very recently, like 3 days ago, in the end of August and earlier in August, just as a demonstration that the ICDR has data continuously to present time. Okay, I hope it was useful and you can inspire some of you in accessing our data. The second notebook I wanted to show you is how to use the CIS index, so the OC 420 data that Signe presented. Here, we are not doing any climate analysis. We are just accessing the data, again, through the URL. So here you have the URL to the netcdf file. You use X-Array to open the dataset, and you can do directly some plotting. So here we did the 40 years of the CIS index for the southern hemisphere. You can ask X-Array to decompose the time series by year, and then you can plot by year. So here is then an example of the southern hemisphere's daily CIS index made from our data in a Jupyter notebook. And finally, if you want to have fun, you can plot the same data, but as a spiral plot using Python polar coordinates. And then you have this type of spiral plot that is well known for temperature and has also been used in the past for sea ice. All right, so as I was saying, this is all in at my GitHub repository, and other notebooks that you might want to check out by yourself is a notebook we made to remap the OSI SAF CIS concentration CDRs to other grids, and also to show how we can process and plot some monthly CIS concentration anomalies. All right, that was it. I hope you enjoyed.
Thank you, Thomas. I think we can go directly to the questions, maybe. No question at the moment.
While people think of question, I think I can say I hope it was useful. It's difficult to judge the level of presentation, so we try to be very simple and an introduction to the data. But there's much more detail on each data on our reports and the publications. And then we are always very happy if you contact us either by email or through the website, as Gwenaël showed, to ask questions or give some feedback.
So another question: why does sea ice extent and type like climate data records? Maybe Signe can answer that too, no?
Yes, and the OSI SAF product archive, we do not make the climate data record for sea ice edge, which I assume you meant, and the sea ice type. We have the near real-time product, but the experience we have from the OSI SAF near real-time product, we have used into the Copernicus climate change service, where we actually produce a climate data record for both sea ice edge and type. So the algorithm behind the Copernicus climate change service CDRs for sea ice edge and type is very similar to the OSI SAF near real-time products. So in fact, we do have a climate data record for sea ice edge and type, but it's in another project. The next question about using scatterometer, maybe that goes for... We do use scatterometer for several of our products in OSI SAF. We have multi-sensor products, for instance, for the near real-time products of sea ice edge and type and drift. But when we are considering the climate data records, we have not included the scatterometer data because we have focused on getting the longest time series, and the time period we have scatterometer data is shorter than the time period where we have passive microwave. But this is on our to-do list. We would like to include scatterometer data in the climate data record as well. Then
The question about the drift, is it possible to merge OC 405 and OC 455 drift data sets?
Yes.
And that was for Thomas.
So it is possible. Technically, you can do it. You have to work your way to it because they are not the same grids, not the same temporal extent. So as Emily mentioned in the passing, there is a notebook available. The link is in the presentation, and that one will help you because it's all about rotating vectors. So on a technical basis, this is possible. I haven't tried to check the temporal consistency of OC 405 and OC 455. So for the time being, I can just say that if you need it, you should try it, and you should make sure or check the consistency in the overlap period. My guess is that on monthly mean ice drift, maybe this works, but I wouldn't go for the daily ice drift statistics.
Thank you. There's a question then about do you include Baltic sea ice concentration into the sea ice index calculation? Yeah.
So when we do the hemispheric sea ice index calculations, so for instance, for the Northern Hemisphere, we would include all ice concentration data we have, that is also including the Baltic sea ice concentration. I'm not sure if this question is regarded into if we have a regional sea ice index specifically for the Baltic. We do not have that at present, but that will be part of the upgraded version 3, where we will include more regions into our catalog of regional ice indexes. I hope it answered your question.
And then the difference between the version 2 and the new version of OC 450 and 430A.
Yeah. If only I had written this paper, then I could just send you the link to the paper. That paper doesn't exist. The paper that introduces V3 and compares it to version 2. But in brief, we have improved the way we tune the algorithms, and the presentation was too fast, but we can show that there is less bias in the new version than in the previous version, especially on the southern hemisphere. High concentration sea ice concentration, we were maybe 2% bias, and now we are 0% bias. So that's one thing. We also reduced the uncertainty, especially over open water. And we achieved that by, instead of using ERA interim, which was version 2, we have been using ERA 5 in version 3. So we're happy with the result, but it was not much of an effort for us. But with the version 3, we are using ERA 5 and ERA 5T, and that really makes a difference for the accuracy over the open water. I think that's really the main differences. What we tried, and I think we managed, is to keep the same format and the same grid. So for our users, it should be very easy to move from version 2 to version 3.
Also, it's upgraded in time.
And also, as Signe says, of course, it's a longer time period. So the question is, between the CDR and the ICDR, what is the difference between the two if they are produced with exactly the same algorithm? Except, okay, so they are indeed produced exactly with the same processing chain and the same algorithm. However, the input data is different. So for the CDR, we used what is called the fundamental climate data record of brightness temperatures prepared by the EUMETSAT CM-SAF. So these are homogenized data records of the brightness temperatures. But for OSI 430A, the ICDR, we do not have this FCDR because it's live data. So here we use directly the operational stream of SSMIS data. So that's one difference. Another difference is that we are using ERA 5 for the CDR, but for the fast track files of the ICDR, we have to use ECMWF operational IFS data. I hope you heard me, but yeah.
Yes, we could hear you, Thomas.
Very good. Then another question. It has been said that CS concentration CDR is reprocessed as compared to the near real-time product. How different are those two after the reprocessing? Yes. So we really have two different processing chains. One is for the ice concentration near real time, and one for the CS concentration climate data record. And of course, the algorithms are quite similar, but they do also have some differences, which is why, because the users asked for it, we have been doing this fast-tracked ICDR, which is 2 days delayed, so that we really have up-to-date but still climate-consistent CS concentration data in the climate mode. So how different are those? They are quite different if you compare two products for a given day. Which is the most impacting between wind and ocean currents for the sea ice drift? Yeah.
Well, the wind is the one that is actually used in the model as a, we use the wind data in the model. The currents, we actually retrieve parameter files of geostrophic currents. It's my understanding that the currents are more stable and so can be treated in that way as monthly parameter files, whereas the wind is the daily, is what impacts more on a daily variation. And this sort of equation and the complicated explanations are in the algorithm theoretical basis document, so you can read some more about it there.
Indeed. Question from Luisa. Hi, Luisa. On the slide of the CS drift CDR, you noted a true resolution of 120 kilometer in contrast to the 75 kilometer grid. Could you give a few more explanations? So indeed, so what happens is that we are retrieving sea ice motion vector every 75 kilometer, but the region of the image we use to track that motion is larger, is about 100 by 100 kilometers. And so there is an overlap of signal between two neighboring vectors. So which is why we do not have exact numbers, but which is why we do not think that the true resolution of the ice motion information is really 75 kilometer. It's probably a bit closer. And if someone wants to study the true scale of this ice drift information and give us an answer, it's very welcome. But we didn't do that study.
Okay, so there's a question why sea ice extent is more often used than sea ice area. This is a really good question. The two indexes differ, as I explained, and they have different strength. So sea ice area will more capture changes in the area when we have a reduced concentration, which is still above 15% concentration, but you see a reduced concentration, which we often do now in summertime in the Arctic. We see more or less the whole sea ice cover have a reduced concentration, but it's still a concentration more than 15%. This will not be captured very well in the sea ice extent, but it will be captured more in the sea ice area. So why do we use sea ice extent more? I think it's for historical reasons. It's been more common to use it, but also since the sea ice area is more affected by noise and uncertainties. Again, in the summer period, the sea ice concentration is more affected by melting at the surface and other disturbance. So the uncertainties on the summer data is higher, and therefore that will be propagated down to the sea ice area in a larger extent than to the sea ice extent. So they have different strength, but when using the sea ice area, you should be aware of that uncertainties can be higher. So that's also a reason for using sea ice extent more.
Thank you. A question from Reid Fischer. Hi. What is the main difference between OSI SAF CDR and NSIDC CDR passive microwave ice concentration? So I don't know all the details, I must say, so we will keep it at a main difference level. Some things we noted, at least, is that we do not, so the OSI SAF and NSIDC do not use the same algorithms. So OSI SAF uses an own algorithm that was also contributed to from CCI, while the NSIDC CDR uses Bootstrap and NASA team, and then they merge the two. So they are different algorithms. And I think, if I'm not mistaken, that the NSIDC starts from daily maps of brightness temperatures, while we do process individual orbits of ice concentration before we integrate them. And then, of course, they are not exactly the same grid, since the NSIDC is using, as far as I know, a polar stereographic grid, and the OSI SAF an Easter grid. So all in all, there are differences, and there are publications that explain the differences, and there are publications that compare the two datasets and others. I hope it was some part of the answer. Emily?
Yeah. Can you explain more on how to generate sea ice drift during the summertime? Well, it is generated from a model, this free drift model, and we use as input to this ERA 5 wind reanalysis and the AMSAR AMSAR fields of ice drift over the summer period. So we're using the main algorithm to create these AMSAR drift fields in the summer, but the earlier period of the CDR, when we only have SSMI data, these don't really describe the summer drift very well. So by using this AMSAR training data and feeding it into the model together with the wind, we calculate backwards in a way to create these parameter fields of wind transfer coefficient and geostrophic currents and turning angle. And then these are per month fields, which we then use plugging into the model again just with the wind, and that gets us the summer ice drift. So there's a lot more details about this in the algorithm theoretical basis document. So have a look at that, and any more questions, please just do contact me, and I'll try and go in more detail.
Yes, there is the ATBD, and there's also the manuscript that was published at Earth System Science Data, so ESSD. what is the smearing uncertainty in OSI SAF ice concentration. So there are several terms that contribute to the ice concentration uncertainty, and we have identified two of them. One is the uncertainty of the algorithm, so it's because of the type points uncertainty. That's what we call the algorithm uncertainty. And the other one is the smearing uncertainty. And in smearing uncertainty, we put what comes from geometry. So for example, with passive microwave, we are combining two microwave channels, one around 19 gigahertz and one around 37 gigahertz. So sorry if it's too technical, but the point is that those two channels do not image exactly the same location on the ice. One is higher resolution than the other. And so because they do not look at exactly the same ice, there is an uncertainty that comes from that. Also, in the smearing uncertainty, we put the geometric effect of the gridding. So you have a field of view which is maybe 50 kilometer in diameter, and you grid that to 25 kilometer grid. That introduces an uncertainty, and we put that into the smearing uncertainty. And so if you take a look at the smearing uncertainty fields in our products, you will see that it's mostly 0 over the open water, mostly 0 over the ice, but it has high values focused on the ice edge, because that's where these geometric effects have higher impact on the uncertainty. Yeah.
So when we're talking about the ice drift products, we're talking about two different products. We're talking about both single sensor products from SSMI and AMSA, which in a way the purest products, and then we're talking about this merged multi-sensor product. So in the merged multi-sensor product, all the vectors are in a way corrected to 24 hours, but in the single sensor product depends on the exact trajectories of the satellites. So the ice drift vectors between two consecutive passes of the satellite can be not exactly 24 hours. And that information is given in the files together with the single sensor products. So if you're wanting very exact time spans for each individual vectors in those single sensor products, that information is available. And if you want a very sort of, in a way, less accurate in that sense, but simpler to use product, then you can use the multi-sensor product where these vectors are corrected to be 24 hours. Do you have anything to?
Perfect. And then again, about real resolution versus grid spacing. So indeed, our OSI 450A and OSI 430A is gridded at 25 kilometer, but we do state that the real resolution is probably 50 kilometer. Again, we don't know exactly what the real resolution is. And again, please help us if you have techniques to answer that question. But really what we want to express is that even if we have a 24 kilometer posting, the resolution, the information content is coarser. I want to underline that this is not just for the OSI SAF product, it's for all CS concentration products that use passive microwave, those passive microwave missions, unless they have done some clever tricks with resolution enhancement. But otherwise, as a user, you should really question when a satellite provider gives you a 25 kilometer product from a coarse resolution input. And here we do write in our documentation attention, the real resolution is probably coarser. No more questions. That was really a nice session. Oh,
Indeed. So I think if we have no... Oh, there is one last question, Perry.
Yeah. Is there any weight function when merging ice drift vectors from different satellites? Would one of them be more important? You want to answer?
Yeah. Yes, so we use the uncertainties from the buoys to find a per sensor weight function in a way, and then can weight using the uncertainties to give this optimal merging in the merged product. I think that's
it. And so would one of them be more important? We found by the validation that the ice drift from the IMSR missions are validate better, and so they have lower uncertainty and they will have more weight in the second part of the climate data record. All right.
Okay. So I think if there is no more questions, then we can close this webinar. Thank you everyone for joining in, and thank you guys in Oslo to have answered this. That was, I think, very nice for everyone. Yeah, maybe.
Yes. Thank you so much, everyone. Very good questions, and we are here if you have more questions or more feedback on our data. Glad you liked it. We liked it a lot.
Yeah, that's really good.
Bye, everyone.